All right, let's continue programming our physics engine. So today we're going to talk about angular velocity and angular acceleration and rotational physics. We want to make our objects rotate in a physically accurate manner, and today we're going to implement that into our engine. So let's go to the article I've been using as a reference for all of this, the mathematics that we're using. And that's on the Chris Hecker website right here. I'll have a link to this website down in the description of this video. But this is the article or series of articles that I've been using as a reference for all the mathematics for this physics engine. And if you scroll down here, he's got 4 articles. Definitely read these if you want to get a better idea of how this all works. But the main one I've been using is this, or the main 2 I've been using are this angular effects article, part 2, and then part 3 collision response. And most of it coming from part 3 collision response. Let's go ahead and open up this article and let's see what we need to do next. So basically what we want to do now is change our physics response algorithm to take into account the actual point of collision and then apply angular acceleration and linear acceleration based on where that collision happens, reference to the center of the object. Okay, let's scroll down here and we can see what that looks like. So this is an article we've referenced before in this video series. And if I scroll here, you can see here's our initial impulse calculation, this J value. So here's how we're calculating impulse currently. Now, if we scroll down just a little bit, we come to this heading here called spin out. And here he starts talking about rotational physics and rotational acceleration and velocity. And we can see a formula for that right here. And we'll use that here in just a moment to apply angular acceleration. And you can see it's very similar to the velocity or how we increment the linear velocity over here. The velocity is incremented by the magnitude of the impulse times the normal divided by the mass. Now, in order to accelerate the angular velocity or the rotation of this object, we increment it by something called the R value of AP. And basically what this is, it's a value that points from the center of the object to the point of intersection, or where is the actual collision happening. But you can see here it has this perpendicular symbol, so it wants the perpendicular value, and we'll talk about that here in just a moment. But this R value times the J magnitude, or the magnitude of the impulse, times the normal, and then we divide that by the impulse. Okay, so that's going to be our acceleration for the angular velocity. Now if we scroll down here, he actually comes out with the full formula for our magnitude of impulse, based on the point of collision in two-dimensional space. So this J formula is the one we're going to want to now implement in our current engine. All right, let's go back to the code and let's go ahead and implement this. So I'm going to go back to the flat world class. I'm going to scroll down here. Here's our ResolveCollision function. This is the one we're using currently, and I'm going to rename this to ResolveCollision Basic. So this is basic collision resolution without rotation or any friction or anything like that. Now if I scroll up, here's our narrow phase, and this is where we actually call the ResolveCollision function. First of all, we're finding out if the bodies actually collide, we're separating them, we're finding the contact points, and then we're resolving the collision. And in this case, this is going to be ResolveCollision Basic. But now let's make a new function right underneath the ResolveCollision function. I'm going to call this ResolveCollision with rotation. Okay, and again, we're going to pass in the flat manifold. Since we're now calculating the contact points and we're calculating the inertia of our bodies, we have all the information we need to now make the bodies rotate in a physically accurate manner. In a previous video, we actually implemented the inertia calculations. So if you want to see how that's done, we made inertia calculations for our rectangle bodies, our box bodies, and also for the circle bodies. And then we also implemented this function for finding the contact points, which is in a previous video as well. I can link to those in the description of this video as well. All right, so let's scroll down and we've got our ResolveCollision with rotation. So now this is going to be just a little bit more complicated because what we need to do is we need to make a for loop that loops through all of the possible contacts. Because there is a possibility that there are 2 contacts, we need to resolve each one of those 2 contacts. So the first thing I'm going to do is actually just get all the information from the manifold, and I'm going to save them to local function variables. Okay, so this is all the information we were getting previously to resolve our collisions. Now let's go ahead and get the contact points and the contact count. All right, so now we're going to make a for loop and we're going to loop through all of the contact points. So we're just looping by the contact count. So if there are two contact points, we're going to loop through both of them, and then we're going to resolve both of those contact points using our new rotation impulse calculation. Outside the for loop, I want to do a couple things. We're going to calculate the restitution because that's not going to change. So I'm just going to copy that over from the previous function. So the restitution is our e value. It's how bouncy this object or these objects are going to be relative to each other. The next thing I want to do is actually create an array that we're going to use to store the contact points so we can loop through both of the contacts and use them in our for loop. So this is just going to be a flat vector array. I'm going to call this the contact list. And we're just going to give it the contact points. So contact point 1 and contact point 2. Okay, and then we're going to have a few more arrays here we're going to implement here in just a moment. But before we do that, let's go ahead and work on, we want to calculate the actual impulse for resolving our collision using rotation. So now up here, here's our previous ResolveCollision basic function. The first thing we did was we calculated the relative velocity. And we want to do that again, but the relative velocity is actually going to be calculated using rotation as well. Because we want to calculate the relative velocity at the point of collision, not at the center of our body. So right now we're just kind of treating it as the center of our bodies with our basic collision detection. But I want to find the actual velocity at the point of contact, which includes not only the linear velocity, but the rotational velocity as well. So we can draw what that looks like. If I have a couple bodies here, let's say this is our center, and then on the edge here we have our actual point of contact. If our linear velocity looks like this, and our angular velocity at this current time looks like this, we want to add these two together. That'll give us the actual velocity at the point of contact, which includes both the linear and rotational velocities. And if we add those two together, we're just going to have a vector that starts here like this, another vector that's added like this, and then we're going to end up with a vector that looks something like this. So it's going to give us a velocity that represents both the angular and the linear velocities. So right now, the way we're storing angular velocity is basically in radians per second, or how many radians am I rotating around like this every second, which is also a scalar value. But I want to convert that scalar value to a two-dimensional vector. I want to represent that rotational velocity as a linear velocity in two-dimensional space. That'll look something like this. All right, and the way we do that is first we calculate an r vector, and that's a vector that points from the center of the object to the point of contact. Okay, and we'll call that RA. And then we get the perpendicular to that value. And so the perpendicular will look something like this. And it's going to have the exact same length as our r value. It's just going to be perpendicular to the r value. Okay, I'll call that the RA perpendicular. And I can multiply this RA value times the number of radians per second, or the angular velocity, and we can get the angular velocity now as a linear two-dimensional velocity. Okay, and I'm going to call that R perpendicular A. So if we look back at the equation in this article, it wants this R perpendicular value, and that's basically what it's talking about. We're talking about a value that is perpendicular to the R value. If we scroll up here, he also has another image of what that looks like. So here's our R values. They point from the center of the objects out to the point of contact. And then the perpendicular is just what we're talking about, is perpendicular to those different R values. So calculating those perpendicular R values is very simple. It's something we've done in the previous videos when we were calculating the actual intersection between two polygons. And what we had to do was we had to get the edge of the polygon, and then we had to get the perpendicular to that edge. And two dimensions, the way you get that perpendicular value is by swapping the x and y values and then negating the new x value. So let's go ahead and write that up in our code. So we want to get this relative velocity. So I'm just going to copy this code from our previous ResolveCollision function. Let's paste that right into this loop. Now we're getting our relative velocity, but it just has linear velocities right now. So the first thing we need to do is actually calculate our R values. So these are the values that are pointing from the center of the object, or the center of the shape, to the point of collision, or the point of contact. I'm going to call this RA for the first one. And so we just get our contact point, and that's just the contact list at I. And then we're going to subtract out the center of body A. Let's do the same thing for B. Okay, and now we want to get the perpendicular to those R values. I'm going to call that RA perpendicular and RB perpendicular. So all we're going to do is swap the x and y values. And then we're going to negate the new x value. Let's do the same thing for the RB. All right, so now that we have these perpendicular r values, we can multiply that by the current angular velocity of our object, and then we'll get a current angular velocity at this point in time for the object in a two-dimensional vector. I'm going to call this angular linear velocity, and this will be for body A. Now, I don't actually think we have a way of getting the linear velocity from the body, so I need to go back and make a property for that. So we're actually in the flat body here. We have a property for the position, we have one for the linear velocity, and we have one for the angle, but we don't have one for the angular velocity quite yet. So this is going to return a floating point value. Just call this angular velocity. All right, so to get the angular velocity as a vector, at this point in time, we're going to take the RA perpendicular, and we're going to multiply it by the body A angular velocity. Let's do the same thing for body B. Okay, so now that we have the angular velocity represented as a linear velocity at the point of contact with rotation, we're going to add that to our linear velocities, our actual linear velocities of the bodies as well. So right here we have body B linear velocity subtracting body A linear velocity, and that's giving us the relative velocity between the two bodies. So let's go ahead and add in the angular linear velocity for each body. All right, I'm going to drop these down to the next line, make them a little bit easier to read. Okay, that's it. So now we have the actual relative velocity at the point of contact that not only takes into account the linear velocity, but also the angular velocity as a vector too. All right, and now the next thing we're doing here is just like we did before, we're taking the dot product of that relative velocity with the normal. And what that tells us, if that relative velocity dotted with the normal is greater than 0, that means the bodies are already moving apart. And so at this point of contact, we don't need to resolve the collision because they're already being resolved. Now, instead of returning the function, we're just going to continue in our for loop right here onto the next point of contact if there happens to be 2 points of contact. Okay, so now we have the relative velocity. We are actually going to use this again, this relative velocity dotted with the normal. So I'm going to save that value here. I'm going to call this the contact velocity magnitude. Okay, so this is the magnitude of the relative velocity relative to the normal, and I'm just saving this value right here because we're going to use this again in our calculation. So the contact velocity magnitude. So let's move on. We want to now calculate our J value. So this is the magnitude of the impulse. I'm actually going to copy this code here for calculating the impulse. So that'll be this code here. And let's just put it right after this if statement. This actually is pretty much going to stay the same. We're just going to add some things to it. Now, first of all, you can see I'm calculating this dot product of the relative velocity with the normal again. And so instead of doing that, I'm just going to use this contact velocity magnitude and paste that right in here because it's the same exact calculation. So there we have the numerator. Let's go ahead and look at the article again. So the numerator stays the same. Now the denominator is going to be pretty much the same. You can see we're adding the inverse masses there, but then we're also going to add these values over here. And this has to do with the inertia of the objects. The I is the inertia, the N is the normal, and then again over here we have these R perpendicular values. Now we've already calculated these perpendicular values, but we need to dot those perpendicular values, these perpendicular R values with the normal, and then we need to square it. So let's go ahead and pre-calculate those values, and then we can add that to the denominator of our J impulse magnitude. All right, so I'm just going to call this RA perpendicular dot N or dot normal. So we're just going to take the R perpendicular and let's dot it with the normal. Okay, and let's do the same thing for the B perpendicular. Okay, so now that we have those, we can add that to our J value down here. So here's the numerator. The denominator is here. We're adding in the inverse masses or dividing by the inverse masses. I'm going to drop this down. In fact, maybe I'll just calculate this up here and call it denominator. Let me reference the article again just so I can see what I need to do here. So I need to square this r dot n value and divide it by the inertia, or we can multiply it by the inverse inertia, which we already calculated in a previous video. Okay, so we're going to add in the RA perpendicular dot n times itself, because we need to square it. Let me put these in parentheses, and then I need to divide by the inertia of body A. Now, instead of dividing by the inertia, we could get a division by 0 here if the inertia happens to be 0, or if this is a static body. So we're going to actually multiply by the inverse inertia, just to make sure we never divide by 0. And a static body is always going to have a 0 inertia, or a 0 inverse inertia, I should say. There's the inertia calculation for the denominator for body A. Let's do the same thing for body B. So I'm just going to copy this code. It's going to be the exact same, just we're going to switch A to B. And I'll drop these down to the next line just so I can read it a little bit easier. All right, so this is going to be RB perpendicular dot n squared, and we're going to multiply that by body A, or this is body B inverse inertia. Okay, so now we have the denominator calculation. That should be our full calculation done there, and our full J value is calculated there. So that should be all done. The only other thing we need to do is this J value, we need to divide it by the number of contact points. So this would be the contact count. So what's happening here is if we happen to have 2 contact points, we want to divide this magnitude by 2, because each contact point is going to get half of the impulse resolution, okay, or half of the amount of the resolution. All right, that's it. That should be our full calculation for the impulse. That will allow us to apply rotation now to the bodies. And the impulse here, the actual impulse calculation as a vector is going to be exactly the same. It's just the impulse magnitude, which is j times the normal. We need to, now that we have this impulse, we need to actually apply the impulse to our body. And we're going to apply the impulse to the body in a linear velocity, as a linear acceleration, and as an angular acceleration. And so I need to make another for loop. Right after we calculate these impulses, I then need to have another for loop where we loop through and actually apply the impulses, okay? So we have one for loop where we calculate the impulses, and then we have another for loop where we actually apply the impulses. Now, in order to make that happen, I need to save these impulses in the for loop. So let's make another array. This will just be a flat vector array. We're going to call this the impulse list, and it's going to have possibly 2 values here. So just be an impulse list of a vector of 2 items. And then right after we calculate the actual impulse, we're going to save that impulse to our impulse list. All right, so at impulse list index I, we're going to save this impulse here. All right, there we go. So now we're saving the impulses. Let's loop through all of the contact points again, and let's apply the impulses to the actual bodies as well. Okay, so in this next for loop, let's get all the impulses that we just calculated. So now the reason I'm doing this in a separate loop, I don't want to apply the impulses until I've calculated the impulses for both contact points. So the problem being, if there are 2 points of contact, if I actually apply the impulses inside this first for loop, when I go back to the next point of contact and I calculate the new angular velocity or relative velocities, it's going to be off by a little bit because I've actually changed the velocity. And what I want to do is, before I change any velocities, I need to calculate both impulses. And then once I have both impulses, I can then apply both impulses to each of the contact points. Okay, so down here we have the impulses. All right, so let me go up here. I'm going to go back to our previous calculation. So here's where we're applying the impulse to our linear velocity. I'm going to copy that out of our previous function. Let's paste it right in here to the second for loop. And this part does not change. The linear velocity is just incremented by the impulse times the inverse mass. I'm actually going to change the way this looks a little bit. Instead of decrementing the second one right here, I want both of these to be an addition function. We're just incrementing or increasing the linear velocity by whatever the amount is over here. Now, instead of subtracting the amount here, I'm actually going to add a negative impulse. And that code actually just spells out better, or makes it more understandable what we're doing here. We're incrementing each linear velocity The first one we're incrementing by a negative impulse, and the second one we're incrementing by a positive impulse. Now, the next thing we want to do is I actually want to increment the angular velocity as well. So we're going to increment the angular velocity of each object by a certain amount. So body B dot angular velocity, let's increment that one as well. Now, we don't actually have a way of incrementing the angular velocity, so let's go back to our flat bodies. And here's the angular velocity. I want to be able to set these as well. So, and I'm going to make this an internal set. And basically what this means is that only this library or functions in this library can change or set the angular velocity. If you're calling this outside the library, you can't actually change the linear velocity. It can only be done inside of the engine itself. So we're just going to tell the angular velocity that we want it to be equal to a value, and now we can change the angular velocity outside of the flat body. So now we need to increment the angular velocity, and the way that works is we basically just give it, just like we did with the linear velocity, we give it a negative impulse times the inverse inertia. Okay, so just like we did, it looks almost exactly the same. It's the negative impulse times the inverse mass for the linear velocity. In this case, it's the negative impulse times the inverse inertia because this is rotational acceleration. And you can see it's not actually going to work this way because this impulse is a two-dimensional linear value, and we need to convert it to a radian value. So the amount of radians that we want it to accelerate at this point in time. So what we're going to do is actually take the cross product of this impulse with the R value, or that value that points from the center of the body to the point of contact, and that's going to tell us how much angular velocity we need to apply, or how much we need to apply based on the impulse direction. Let me draw what that looks like here. We have these R values, and we can look at this B body here. Okay, so here's our R value for B. Now, if our impulse is pointing exactly the same direction, whether it's that way or exactly opposite direction of our R value, the impulse that we're going to apply as far as rotational acceleration is going to be 0. But the more that the impulse is pointing in a different direction, let's say our impulse points in that direction, now we're going to apply a lot of angular acceleration. And if it's just pointing away just a little bit, that means we're going to apply just a little bit of rotational acceleration. And I can kind of draw that over here as well. So if this is our R value and the impulse is the same exact direction as the R value, there is no angular acceleration. They're exactly the same direction. We're just going to get linear acceleration. If the impulse points something like this away from the R value, then we're going to get a lot of angular acceleration. And we're going to use the cross product to figure out how much angular acceleration do we need to apply based on the impulse. Let's go back to the website here. I have a cross product viewer. So this is actually a cross product viewer that allows us to see the cross product of this AV vector and this BV vector. So the vector pointing from A to B and the vector pointing from B to C. Now the value we're actually concerned with is this last value down here. You can see we're doing A cross B, and then it gives us a vector 3. And the one we're using down here is this last Z value here. So in this case, it's 6. So let's pretend that this A vector, or A to B, is our R value. So this is the value pointing from the center of the object to the point of contact. Now, let's say the impulse is pointing exactly the opposite direction. Right there, we're pointing exactly the opposite direction. So the impulse is the B vector, or A to C. And you can see when they're pointing exactly the same direction or exactly the opposite direction, we're going to get 0 impulse or we're going to get 0 acceleration on the angular velocity. The more the impulse is a different direction, you can see the impulse or the amount of acceleration we get is going to be a lot more. So here we're pointing perpendicular, and when we're perpendicular to the R value, that's where we're going to get the most acceleration, or rotational acceleration here. You can see 8.4 in this case. And on this side, it's all positive. So it's going to apply a positive rotational acceleration over here. Okay, once we're back in line or exactly the same direction, it's 0. And then when we're on this side, it does the same thing. It gives us a rotational acceleration, but these are all negative accelerations. So it's going to rotate the opposite direction, or give you an acceleration in the opposite direction. All right, so let's use the cross product to actually give us the value that we want. So we're going to take the impulse, we're going to do the cross product. So we're going to use the RA value with the impulse. And let's do the same thing for the angular velocity of B. I'll just copy the code right over. The impulse calculation here is negative. For B, it's going to be positive because we want it to be the opposite impulse. So we'll just take out that negative value. And this is going to be the RB cross the impulse, crossed with the impulse. Okay, now the last thing is we don't actually have these RA and RB values, so we need to save those from our previous for loop. Okay, so let's scroll up here, and just like we calculated or we created an impulse list here to save those impulse values, let's save the RA and RB values. We'll just have an RA list and an RB list as well. Okay, so now down inside our for loop where we're calculating the impulses, let's go ahead and save our R values. And we're just going to save these to the R lists. So at index I, this is going to be RA. And same thing for RB list. Okay, so now once we have those R values saved in our list, we can go down here to our actual application of the impulses, or this loop where we're applying the impulses. Let's go ahead and get our RA and RB values. And so now we have everything we need. We're actually calculating the impulses, we're saving them to the impulse list, we're calculating the R values and saving those to the R lists, and then after that we loop through all the contacts and we actually apply our impulses. Our linear impulse application is exactly the same. The angular velocity impulse is now calculated using the inverse inertia of the body, and then we're crossing the impulse with the actual R value to find out how much of that impulse is going to be applied to rotation. All right, so that should be everything we need for that. Let's go ahead and now go back to our game class. Before we run this, we actually took out the ledges, and here's the code for that. We had some diagonal or ledges that were being displayed. I took those out earlier for a previous video. Let's add those back in so then we can see what it looks like. Let's go ahead and run this. All right, so I'm going to drop some boxes into the world. That looks the same. We're adding some things here. I'm going to drop one up here and just see how it looks. Oh, and that's not actually rotating. So let me go back to the code and see what I'm missing here. Oh, inside of our flat world, in our narrow phase, I'm still calling the ResolveCollision basic. We need to call it the ResolveCollision with rotation. Okay, so now we should see some rotation. Let's go ahead and see what that looks like. Okay, so I'm going to drop a body right here on the ledge, and let's just see. Oops, it looks like it's rotating the wrong direction. Let me see if I got one of the signs wrong here. So here's a typo, one of the things I missed. We were incurring the angular velocity by the RB cross RB impulse, but I got body A inverse inertia here. This should be body B inverse inertia. Okay, and that looks a lot better. Okay, so it looks like everything is working there like it should. I'm seeing rotation. Let's stack a body here. That looks right. That looks like it's working just fine. Okay, and if I put a circle here, let's put a circle here and we'll put a box body on top. That looks right. Okay, and that looks all good. I'm seeing the bodies look like they're rotating correctly, and they are falling and rotating off the ledges there. And you can see everything looks a little bit slippery, right? And it's because we don't have friction being taken into account yet. But other than friction, everything looks really, really good. It looks like everything's rotating correctly. Okay, so that is our rotational physics. The bodies are rotating correctly, and they are being resolved with rotation. Now, the only thing I want to talk about now is kind of a C# thing here. So if I scroll up here, we're in the ResolveCollision function with rotation. These lists here, in C#, when I create a list like this, it has to be created on the heap. or when I create an array, it's created on the heap. So I really don't want to create these lists or these arrays right here because every time I do this, I'm creating them on the heap, and that puts pressure on the garbage collector because, especially in a loop like this where I might be doing a lot of these calls, the garbage collector then has to work on removing these every time they're not in use. And that happens every time this function loops. And so instead of creating these values right here or these lists or arrays right here, I'm going to create them in the world class itself. So let's copy this code out of here. At the top of our world, let's go ahead and create these arrays. Okay, and I'm going to make these all private. All right, now inside the constructor, let's go ahead and create the arrays. Okay, so all I'm doing here is I'm creating the arrays one time. So basically we're setting aside the memory inside the world class, and then we're just going to reuse the memory. That way we don't create arrays every time that we're resolving collisions, okay? And we're going to keep pressure off the garbage collector that way. So let's scroll down here inside of our ResolveCollision function. Now, instead of creating these arrays every time inside of this function, we're just going to reset the values of these arrays. So let's do that for each one of these. So the contact list 0 is just going to be the first contact count, or the contact point. Same thing for contact list at index 1. This will be contact 2. And the rest of these lists, we just need to reset the values. So I'm going to loop through the contact count. The impulse list at index I is just going to be, we're going to set that to a flat vector 0. The RA list, we're going to do the same thing at every index. We're just going to set it to a flat vector 0. And all we're doing is just resetting the values. So we've reset the contact points, we reset the impulse list to 0 and the RA list to 0, and then we can just get rid of this code. Okay, so now we're not actually allocating memory every time. We're just allocating the memory once the flat world is created, and then we can reuse that those values, or reuse that array every time and not have to allocate the memory. Let's just run that and make sure it works like we're expecting. Okay, and that looks exactly the same. I can throw a couple circles in here and see what that looks like. And we can throw a bunch of bodies in. You can just get an idea of what's happening here. That is how you implement rotation into your physics engine. And that is the code for rotation. Now, we still don't have friction, and so the objects, the circles here, even though they're sliding along, they're not actually rotating. And I can add one more thing to our code here, just so we can see what that looks like. So let me close this out. And one last thing I'm going to do is let's go to our flat entity, and here's where we're drawing the shapes. I'm going to add some code here that's going to draw a rotated line on the circles. So it's going to be a line that points from the circle center to the edge. And it's going to, that line is going to move based on the rotation of the circle. And so then we can see if the circles are actually rotating or not. Okay, so I need two vectors, and these vectors are the endpoints of the line I want to draw. It's going to start at the center of the circle. I'm going to call VA, that'll just be the center. And so that'll be flat vector 0, or actually a vector 2, 0. Since we're using monogame to draw, these are monogame vector 2s. Now, VB is going to be the other endpoint. That's going to be at the edge of the circle. And all that's going to be is the, on the X, it's going to be the radius of the circle. So we get the body radius. And on the Y, it's going to be 0. Now that I have this vector pointing from the center out to the radius, let's go ahead and transform it based on the transform of the body itself. And this is a transform class that comes with our drawing routines. So the new transform is going to take the position, and it's going to take the rotation. And actually, that'll be the angle of the body as well. All right, now that we have this transform, let's transform the VA and VB. All right, now that we have the transformed line, let's go ahead and draw it. So we're just going to, after we draw the circle, we're going to now draw a line. And we'll just make it a white color there. Okay, and so quite a bit of code added there, but all we're doing is we're making a line that points from the center of the circle out to the edge of the circle. We're transforming it based on the transform of the body itself. and then we're going to display it as a line on the display. So let's go ahead and run that. You should see a line, or we should see a line that points, we should see this line on the every circle now. We're not actually probably going to see any rotation or very much rotation because there is no friction, and friction is what is required to make the circles rotate for the most part. Okay, so let me drop a few circles in here. And you can see the line is there, but they're not actually rotating. They are bouncing and moving, but since there is no friction, the circle has no reason to change its rotational velocity. Now the boxes will change because they actually experience a change in rotation, but the circles don't experience that at all. All right, so that's it for our rotational acceleration and rotational physics.